So today I will present a paper titled MACAO, a maliciously-secure and client-efficient active ORAM framework. So this is the joint work with Jorge Guajardo and Attila Anteyavu. So let's first begin with some basic concepts. So first, what is ORAM? So ORAM stands for Oblivious Random Access Machines, which is a cryptographic protocol that allows a client to hide access pattern when accessing the data that's stored in the untrusted memory. So basically, given the logical read or write operation, so ORAM protocol will translate such a logical operation into a sequence of physical read and write operations in such a way that by observing the physical read and write operations, the adversary cannot infer what's the underlying logical read or write operation. And ORAM has been used in many applications. For example, ORAM has been used for the cloud storage as a service, where the user can privately query the data stored on the cloud. ORAM also has been used to seal the access pattern leakage in structural encryption. And also, ORAM has been used in the secure multiple-party computation in the RAM model. So let's take a look on the timeline of the ORAM. So ORAM was first introduced by Goldrich back in 1987 for the software protection. And since then, many attempts has been proposed in reducing the ORAM communication overhead. So one of the most famous ORAM scheme is Path ORAM, which appeared in CCS back in 2013, that can offer the logarithmic communication overhead. And this has been proven to be the lower bound of communication for a single server ORAM. And however, the O-log and communication overhead has been shown to be kind of still costly for certain applications. So that's why in recent attempts trying to reduce the communication overhead to a constant. And there are three representatives here. So the onion ORAM, which offer the constant communication overhead by using the homomorphic encryption. And also the ring onion ORAM also leverages homomorphic encryption to achieve the constant bandwidth overhead. And another work is S3 ORAM, which also features the constant bandwidth overhead by using the distributed setting. So however, there are certain limitations in this work. So first of all, onion ORAM, even though it offers the low communication overhead with malicious security, it's based on a homomorphic encryption, which incurs very high delay due to the high computation. And the malicious security is achieved by using the cut and choose techniques, so which also incurs the communication and computation overhead at the client side. And on the other hand, the S3 ORAM, even though it features very high efficient computation, however, it only offers the semi-honest security. So the question is there any way that we can propose a new ORAM scheme that can feature the low end-to-end delay and also with active security? So before going to our MACAO framework, I would like to give some fundamentals about the ORAM thing. So first is the three ORAM paradigm. So this is the paradigm that most efficient ORAM scheme to that following. So this is based on the binary data structures where we organize the data, that we put the data into the tree. So the real data will be located somewhere in the path on the tree. And because there are more nodes than the number of actual data, so we fill with the empty nodes with some kind of dummy data. And in the three ORAM paradigm, there are two general, the general access protocol incurs two general phases. First, for example, when we want to access to block A, so we get the path ID, the path information of this block from the position map component that is stored in the client side. And then we read the path by using the retrieval protocol. And the path will be stored somewhere at the client side in the temporary cache, like stash, for example. And then we update the A if possible, if we need it. And after that, so we randomly select the new path of the block we just accessing. For example, in this case, the new path of A will be assigned to 4. And then we execute the eviction protocol in order to write the block that we just accessed or some block in the start back to the tree. And the eviction protocol will try to push all of the block from the upper level to the deeper one in order so that we have an empty room for the later eviction. And there are some security concerns in terms of the malicious adversary for all of the PIR-based ORAM. So this is because of the unit vector created in the retrieval phase, as you can see in the figure. So the characteristics of this unique vector is that so it only contains one element of 1, while the other are 0. So you can see that due to the dot product, so the adversary can tamper the block that corresponds with the element 0 without impacting the correctness of the computation. So in this case, client cannot tell whether the adversary have tampered with the data in order to compromise the correctness. And due to this reason, so the adversary can learn the real block position. For example, in this case, the adversary can learn that the real block is located at the leaf node. And this violates the ORAM security because we can leak the access pattern in this case. So to fix this issue, so we propose the MACAO framework, which is based on the authenticated additive secret sharing. So the authenticated additive secret sharing, basically, so given a secret X in this case, so we split X into the two pieces, X1, X2, in such a way that X is equal to X1 and X2. And a value X is called authenticated share if each party stores 3 components, share of the value X, XY in this case, and the mark key, the share of the mark key, and also the share of the mark of the secret. So in this case, alpha is considered as the random global mark key, so which can be generated by the dealer in the multi-party computation setting. And the authenticated share of a value is denoted as the X in the angle bracket, which contains 2 components, the share of the secret itself and the share of the mark. And based on the homomorphic property of the secret sharing, so any linear function that can be computed locally based on the share value. For example, we have the constant in this case, V1 and V2, and the share value, so we can perform all the linear combination locally. And also in MACAO framework, we harness the secret ORAM eviction principle along with the permutation matrix in order to achieve the high efficiency. So the circuit ORAM eviction principle allows us to set the block bucket size to be very small, which is, for example, 2 in this case, you can see. And the eviction principle in secret ORAM is that so we only perform 1 scan from the root to the leaf of the path. And for each level, we only pick or drop at most 1 block. And at any time, so we can hold at most 1 block on hand. So you have to decide whether we should drop the block that we are holding before we can be able to pick a new block. And in order to realize this eviction principle, so one way to do it is to create a permutation matrix of size z plus 1 times z plus 1, and in such a way that so we set a certain element in the matrix to be equal to 1. For example, ij z plus 1 equal to 1 if we want to pick up the block at the index j in the current bucket, or we can set i1j equal to 1 if we want to drop the block that we're holding to the index j, or i1g plus 1 equal to 1 if we want to move the holding block to the next level. So in this case, we don't drop or pick any blocks in this level. We just skip this level. And finally, we set ij plus 1j is equal to 1 if we want to keep 1 block in the position j, so we don't move it. So by creating this permutation matrix and we using the multiplication protocols, we can be able to perform the eviction with the secret ORAM eviction principle with least client intervention. So in MACAO framework, so we propose 2 main schemes. The first one is called a PAR ISSS. So the PAR ISSS is based on replicated secret sharing, which is specifically designed for the 3 server with the honest majority. So meaning that it's only 1 server and malicious in this setting. And on the other hand, another scheme is called a PAR speed, so which is based on speed secret sharing scheme. And this can work in the general L server setting with this honest majority. So L in this case can be small h2, and we can adjust this in order to achieve the higher privacy level. So let's talk about the pi-ISS scheme first. So the retrieval phase. So we have two ways to implement the retrieval phase efficiently. The first one is based on XOR PIR, which is the private information retrieval techniques using the XOR techniques. And the way to do it is that, so given the select query, like this, so we create a pair of PIR, XOR PIR query for each authenticated share. So in the figure on the right side, so the data layout in each server. And you can see that each server stores two shares of the data, and they are replicated to each other. Like S0 stores T0, T1, S1 stores T0, T1, T2, and S2 stores T2 and T1. And for each authenticated share stored in two servers, so we create a pair PR query. So the PR query is just a random string, as you can see here. The first query is a random string, and then the next query is we just perform XOR between the random string and the select query that we just created. And then we send these two queries to the corresponding server. Server reply by performing the XOR operation locally and get the result, send the result back to the client. So we do the same with the other two shares of the database in different server. And the other server also do the same thing. And finally, we obtain three authenticate share of the block that we want. And at the end of the protocol, so the client will reconstruct the authenticated block by perform the local addition. So in this case, X and Y, X is actually the block that we want to retrieve privately, and Y is actually its mark. And the client will verify its correctness by computing alpha X, whether it's equal to Y in this case. So that is XOR PR protocol. And the other protocol that we can implement in the pi-ISS scheme is that we base on the replicated secret sharing PIR. So this is slightly different from XOR PIR in the sense of how we create the PIR query. So in this case, we create the replicated secret sharing PIR queries based on the underlying identity secret sharing scheme. As you can see here, so given the select query, we split it into the 3 pieces, and we send 2 pieces out of 3 to a server accordingly. And the server will perform the local multiplication and addition and send the result back to the client. And at the end, similarly, so client will sum up all together to obtain the retrieved block along with its mark. And finally, the client will verify its correctness by recomputing the mark and verify with the mark that it received from the server. And for the eviction phase, so in MACAO's framework, so for the pi-ISS scheme, so it is based on the matrix multiplication protocol that we designed using the replicated secret sharing. And the detailed protocol, as you can be seen here. So basically, so by following the circuit ORAM eviction, so we will create the authenticated share of the block which we want to evict, along with the share of the permutation matrix that I have introduced previously, and the client will send it to corresponding server like this. Server will interact with each other to execute the matrix multiplication protocol. And at the end of the protocol, so all the client and server will come together and execute the mark check protocol to verify the eviction integrity. And the mark check protocol in this case is based on the random linear combination, which allow us to check a bunch of authenticated share at once. So in this case, the client doesn't need to download the entire matrix, the matrix output. It's just only download a value, which is a random linear combination of all elements of the matrix. So this significantly saves the communication. On the other hand, the pi speed scheme, so this one purely relies on the matrix multiplication protocol, which is built on the speed secret sharing. So retrieval phase and eviction are purely based on the matrix multiplication protocol, in the sense that we can interpret the select queries as the column matrix, and then we use that to multiply with the path along the path. And in this case, server only execute the the magic multiplication protocol in order to perform private retrieval and private eviction. So in this guy, and one thing to note in the speed scheme is that it's based on the online-offline computation model. So it requires us to have a triplet called as multiplication triple, like this, so which are pre-computed in the offline phase in order for this protocol to work. And the authenticity of this protocol is based on verifying the correctness of the open value E and P in this protocol. And there are several extensions that I would like to mention in order to optimize the performance of MACAO. So first is the bandwidth reduction tricks. So you can see that for MACAO is based on additive secret sharing. So given a secret A, so we split into the 3 pieces, A0, A1, and A2. And given another secret B, we split it into 3 pieces, B0, B1, and B2. And without the pseudo-random function, so in general case, so client has to send each share to each server. So this will significantly increase the communication overhead linearly to the number of servers that we have. So by using the pseudo-random function, the client only needs to interact with one server. And for the other rest of the servers, so it can generate the share locally. For example, in this case, you can see S0, S1, and S2 the share for S1 and S2 can be computed locally by having a pseudo-random function. So what the client needs to do in this case is just send the seed at the beginning and in the setup phase to S1 and S2, and only send the share of the value of A to S0 in this case. So in this case, so client doesn't have to interact with S1 and S2, and this can help us to significantly reduce the bandwidth overhead. And similarly, in the replicated secret sharing scheme, it requires servers to communicate with each other to reshare the value. So in this case, we also can be able to apply the pseudo-random function technique to reduce the communication overhead between the servers. Another optimization that we have done is how to reduce the client storage. So you can see, due to the secret ORAM eviction principle, so we need to have the slash offside or log_n that was stored in the client side. So for certain applications, this size might be too large to be stored locally by the client. And there are 2 ways to get rid of the stash. The first technique is we trivially follow what has been discussed in the circuit ORAM paper, in the sense that we store the stash at the server side. And to be adapted to this technique, so we can use private information writing technique in order to privately put a block into the stash. And for the retrieval phase, we can simply use the PAR techniques, which we also need to consider the stash as an addition level for private retrieval. Another technique that we can use is we harness the triplet eviction principle proposed in Onion ORAM. So in this case, we don't need to have the stash for the triplet eviction to operate. However, the price to pay for this is that, so we need to increase the bucket size to be O log n. So by increasing the bucket size to be O log n, so we might increase the computation I/O access overhead of the retrieval phase in ORAM 2. And let's move to the performance of the MACAO framework. So you can see that, so we fully implemented our MACAO framework under C, and we performed the actual experiment where we set up the servers to be Amazon EC2, that's relatively close to each other. And here is the result. You can see the highlight one is actually the performance of the MACAO schemes compared with other ones. So we achieved around 7 times faster than the single server ORAM, and MACAO was around 1.5 times slower than the S3 ORAM. The reason for this slow is that in MACAO, so we have to process 2 components. So first is the data itself, and the second one is the MAC component. So in S3 ORAM, there is no MAC component because it only offers the semi-honest security. And also MACAO scheme, for example, the speed one only requires 2 servers to operate, compared with the 3 servers in the S3 ORAM. And here's the insight where we dissect the total cost to see which factor that contributed most to the total delay of the MACAO scheme. As you can see, the most overhead was coming from the server computation. And this contributed the most portion to the overall delay. The second insight is that bandwidth is also another factor that impacts the total delay. However, with the bandwidth reduction trick based on the PIF function, so it significantly reduced the communication overhead. And here's another experiment where we experiment a MACAO framework with a higher privacy and higher number of privacy level. So in this case, so we only perform the experiment with the Pi speed scheme because the Pi RSS scheme is specifically designed for the 3-server setting. So if we increase the number of servers for the Pi RSS scheme, so it significantly increase the storage overheads too. So that is not desirable for higher privacy level. So that's why we only select the Pi speed scheme to do this experiment. And you can see that the bandwidth reduction trick also have in this case. So this is because the bandwidth overhead does not depend on the number of servers in this system. So we only send the data to one server, and for the other server, it can be locally computed with the PIF function. So we don't need to interact with other servers from the client. So that's why this is the factor of difference between two schemes with and without using the PIF function. And here's we zoom to the conclusion. So in this work, so we have proposed the MACAO. This is one of the first multi-server active ORAM frameworks that can provide the integrity, attach pattern obliviousness against the malicious adversary. And one critical feature that I forgot to mention is that it's also allow the secure computation over the access data. This is because the access data is in the form of secret sharing, so you can perform further computation like addition or multiplication after you access the data. And this is based on authenticated identity secret sharing and the 3 ORAM parallelism. And our future work is that, so we would like to integrate the MACAO framework into existing distributed file system in order to implement a full-fledged Oblivious distributed file system. I believe, so the figure here is our proposed model for ODFS, where we believe that by using the MACAO, so it is possible to build a full-fledged implementation of ODFS. And the second one is how to build a multi-user Oblivious storage based on the MACAO framework. So these two are our future works to be considered. And I think that's it. And here's the code of the MACAO if you are interested in, so feel free to check it out. Thank you.
OK, I have one question. So basically, for MACAO, how scalable it is if you have multiple servers?
So we have two schemes in MACAO. So the first one is specifically designed for 3-server setting because it's based on the underlying replicated secret sharing. And the replicated secret sharing does not scale well by increasing the number of servers because you need to store more data per server. So it increases the storage overhead too. So that's why it's not desirable for the higher number of servers. But if you see in this figure, so for the speed one, so it can operate in any general number of server setting, as you can see here. So by privacy level, it means we increase the number of servers. So you can see that it's highly scalable with the number of servers by increasing it. So especially if we use the bandwidth reduction trick with a PIF function.
OK, thank you.
Thank you.